Welcome back. Hope you had a good spring break. I had a pretty good one. I got a lot of the grading caught up. I think I'm completely caught up on grading right now, which is special for me. And we had a good time. I made a soccer juggle video for Nick's team. I think you could see it if you like subscribe to my YouTube channel, but I'm not sure how it works because I can't. I don't know how I see what you guys see, but pretty sure if you subscribe, if you want, you could check it out. It's pretty fun. And Sky was the star here. Here she is in Nick's uniform. All right, so today we're going to do announcements. Then Chapter 16, Electrophilic Aromatic Substitution, with the looking at a little more complicated examples than we saw in Chapter 15. And then we might even get into Chapter 17, some carbonyl chemistry stuff. Okay, so spring break's done, and we're not starting total synthesis yet. I know I got that up there, and I even have the total synthesis oral presentations right there. That's not going to happen this week. So I'll keep you posted on that. I'm going to see how much of that we're going to get to. I put out the HPLC data, and I have all the data for experiments that we started before we left, except for the aldehyde enigma, but I'll get to that this week. And then I'll start working on the new stuff for you guys. Don't worry, I'm not going to like slam you at the end of the semester with stuff. We don't have time to get to all of it. We won't. We'll make it work. We will have the lab exam though next week. So a week from this Wednesday and Thursday. And maybe I'll have to poll you guys. How are we going to do that? Do I do it on just what? Do I do it some of you on Wednesday, some of you on Thursday? I don't know. Maybe all on Thursday. I'll let you know. And then I'll provide details for that. That lab exam, I'll give you like real clear, like no, for this experiment, how to do these things and that, like I did last year. And then the exam average was really high, 86%. It's awesome. So there, and the high score individually was 149 out of 150, just missed 1 point. When I was grading this, I could have made mistakes. I was grading it all online. I added a lot of comments, probably too much. That's why it took me hours. But if you guys read through those comments and learn from them, it's a good thing. But if you don't, then I just wasted my time. So check them out and read through it. And then I could have made mistakes too, because it was like, it's kind of weird the way you have to type in the comments and the scores. So check it. Please add up your point total again. Let me know if I made a mistake and we can fix it. And then exam corrections as always, excuse me, with sentences. Do this Wednesday, Thursday. So the exam key, I decided to put it in a discussion for exam 2. So when you go to Canvas, click on the discussion area, and you'll see discussions for chapter 15 and 16, and then chapter 17. I might have added, or I will. And then you'll also see exam 2. When you go to that, it'll have the exam key. And the exam key, the way it worked out, I gave out like 3 different exams, and so there's for some problems there's 3 problems that are similar, and for some it's just 2, so I have a mix of those. So check it out, see which problem you had, but look at the other ones too, learn from them as well. And I have a link to that here as well, but it's in Canvas under discussions. And then after exam quiz, I know it's kind of weird to do that because the exam keys are online, but I'm just going to trust you don't do it because I want those of you who aren't going to do that to get the benefit of it. So you'll take that Wednesday and Thursday. That's another one of those weird ones. Should I give it just on Thursday or Wednesday, Thursday? But I think for this one, I'll give those in Monday, Wednesday lab can take it Wednesday. So I'll like email you, or maybe I'll tell you what problem to get. I'll let you know more details about it, the quiz. And then you might get a different version of the question. So let's say you had the first question was an alkyne nomenclature, and I had 3 different ones. And so you might have gotten one that was like an octine, and then some. But then on the quiz, you might get the heptine one, because I don't remember. I don't want to go through and figure out what each person had, but you should be able to do them all. So check those all out, learn from them, study it for the quiz. And if you want to take your quiz early, just let me know. Almost all of you struggled with the first part of question 2 on the exam. So on my key, you'll notice I wiggled this methyl off of an alkene. What that means is, in this particular case, you have the trans and the cis alkene mixture. That's what you get from an E2. And a lot of you just gave the trans for some reason. But when you have, and then you might not have given the right answer still. The next step for that is a bromination in that, if you look at number 2 on the exam. And when you brominate the trans one, because the bromine comes in anti, it just makes one product. It might not look like it here, but if you rotate around the bond, you'll see this is a meso compound. So if I were to draw this with a wedge here and a dash there, it's the same thing. So when you have a transalkene, you just get the one meso product. If you have the cis, you'll get the 2 enantiomers. These guys look real similar, but they're not. Calculate the RNS, you'll see they're not. So you get a pair of enantiomers from the cis alkene. In our case, where you have, you know, this trans and the cis mixture, then you're going to get all three molecules, which you can see here, and you can represent them with the double wiggle. That's the way I did that there. So hopefully that'll clear that up a little bit for you. If you're not sure why these are different and stuff, add the RNS. Okay, now I want you to turn in all your old labs this week if you have not yet. So you should be able to turn in all of these reports I've listed down here, because I didn't put Grenier data on there, but I think everybody has that data. They should, because I've asked multiple times. So, and then, but for example, the 2D NMR, you might not have had time to get that data, but it is online, so use it. It's in the lab guide area. Polarimetry data is online, distillation, banana oil, biodiesel, and HPLC and Diet Coke. This one took me forever to make, but hopefully you like it. It's got some good stuff in there. So try to knock all those out. Some of you haven't been turning in labs. That's not good. Let's go. This is the redemption week. We'll get that stuff done, and that's going to help you with the lab exam too next week. All right, you'll find this data for these guys under our lab guides on our Google Sites. And some of you haven't turned in homeworks as well. Let's just get stuff going. We had a break. Let's get rolling again. Turn in those homeworks. Those of you who did turn in the homework, you can see on average they did better on the exam. So let's do that. And then students who came to my Zoom sessions, I've got a lot of you who come into the Zoom sessions, and we're getting a lot done there. It's really helping. And it's kind of nice, because normally when we have lab on campus and I'm busy doing that and training students on instruments and things, I don't have as much time in office hours, so you wouldn't get as much one-on-one time with me or small group with me. But now you can get way more time with me. It's like you're really lucky. You can get like the perfect tutor for this class, since I write the exams for you know, I don't know how many hours a week I do the Zoom office hours. I do a lot. So take advantage of that. If you haven't come to the Zoom session, start coming. And then ask your friends who do, because they've all did really well in the exam. And then this England extra credit thing I gave you, it's related to the electrophilic aromatic substitution stuff we're going to do today. I'm going to make it mandatory. So it sounds silly. It's extra credit and it's mandatory, but it'll help you a lot. So I want everybody to do that. You read through the thing. It's got some jokes in it, and then you fill it out, and then you turn it in. But maybe before you turn it in, have a friend check it over, and then the friend signs off that they checked it over, and then they turn that in, the checked over thing that they did, and they can get points for it too. So you can get 3 points for your work on it, and then you can get 2 points when you check someone else. So you can get a total of 5 points. So do that, and here's a link to it right here. Got a couple structures up here. Some aromatic rings that have a para substitution here, and this one's para substituted as well. This one is ibuprofen. That's what's the active ingredient in Advil and other pain relievers, a non-steroidal anti-inflammatory. And acetaminophen over here is what's in Tylenol. That's another fever reducer. And there has been some controversy about the coronavirus and the COVID-19, and maybe ibuprofen's not good to be taken, but during that, but it's kind of up in the air. I don't know if there's a lot of hard research about it, but if you get a fever, maybe try Tylenol first. But if it's bad, it's good to be able to go back and forth Tylenol and ibuprofen. But your doctor will let you know about that, and hopefully not. Hopefully you don't need that. But it's pretty cool how to know that these are just simple aromatics like we've seen, huh? Like you can say, oh, this guy right here got a lone pair, can resonate in, withdraw through induction, but resonance wins, so it's affecting the pK of that, making it a weaker acid. Interesting stuff. Let's do a really quick review. I want to make sure you get these overall concepts because they're going to help you for this chapter and for the next chapter. This idea of that an acid and an electrophile are sort of cousins to each other. They both are Lewis. They're both actually Lewis acids because they both accept electron pairs. So if you think about this, an acid, your first acid you might think of as maybe hydronium. And then an electrophile could be something like a bromide, ethyl bromide. And then when you look at the ethyl bromide, it's not as obvious to see how they're similar, but they are. They both have a positive carbon. There's a delta positive there and a delta minus there. The bromine's more electronegative. So it's electron loving, it's an electrophile. And the hydronium's kind of electron loving too, right? Bases come over and react with it. And then the other thing is a base and a nucleophile. They're kind of like cousins too. So let's think of a base. First one that comes to mind is probably hydroxide, correct? And that guy is wanting to deprotonate things. And then a nucleophile could be something like hydrogen sulfide. Hydroxide is a nucleophile too. Hydrogen sulfide is much better in terms of SN2. So both of them they're both actually Lewis bases, huh? They both will donate pairs of electrons. And what about charges? The acids and the electrophiles, they're positive charged, right? Usually, not always, but usually. And the Lewis bases, the base, Bronsted base, and the nucleophile, they're negative charged. So always think that way. Acidic conditions, remember, positive charge, organic intermediates, basic conditions, negative charge. All right, so with that in mind, if you have an acid and it has attached to it something that is electron withdrawing, a group that's going to withdraw electrons from the acid, is that going to make the acid stronger or weaker? Pause, think about it. There you go. That's going to make it a stronger acid. Because it's making it more positive, right? If something's removing the negative electrons, becoming more positive, stronger acid. If you have a different acid that has an electron donating group attached to it, how's that going to affect the acid? That's going to make the acid weaker. And the exact same ideas will apply if you replace in here. If you put the word electrophile in here, same thing applies. If it's got an electron withdrawing group on it, the electrophile will be more positive. It'll be more reactive, it'll be stronger. And same here too, because they're cousins, the acids and the electrophiles. Okay, and then let's look at a base then, a base and a nucleophile. So if you have a base / nucleophile, and you have an electron withdrawing group attached to it, is that going to make it a stronger base and a stronger nucleophile or weaker? So let's see. The bases and nucleophiles want to be negative. You're removing negative charge. That's going to make it weaker, right? Good. And then if you look at the opposite, hopefully this is becoming totally obvious and you're like, you can quit now, but we'll just do the last one here. If I have an electron donating group, then what will happen to the base and nucleophile? Now they're more negative, so they're stronger. Okay, so that concept I hope is not too difficult. I bet it's not. But now let's apply it to more like real molecules. Real examples. So let's look at, for example, we're going to look at the acidity of this phenol when it has a nitro group attached to it. So let's see. We're looking at this acidity. Sorry. My red's not working on the whiteboard, I think. Acidity. So we're going to look at the acid-base reaction of this guy. If something's going to come along and be protonated. So how does that nitro group affect it? Is it an electron donating group or an electron withdrawing group? In terms of induction, is that nitrogen more electronegative than a hydrogen atom? Yes. So this is electron withdrawing in terms of induction. In terms of resonance, is that nitro group withdrawing electrons through resonance? Yep. You can see it swinging out like that. So this is electron withdrawing. So does that mean this molecule is overall, this nitro group, is it overall withdrawing or donating? It's easy. They agree. Overall electron withdrawing. So how's that going to affect that acid? Is that going to make it more acidic or less acidic than just regular phenol? We're always comparing it to just the regular phenol without the nitro with the hydrogen there. So that's going to make it more acidic. More reactive. And you can think of it lots of ways. You can think of it in terms of, okay, the acids and electrophiles are positive, and this is making it more positive, more reactive. You can think of it as removing electron density from that bond, weakening it. You can also think of it when the conjugate base forms. The negative charge that will be here gets stabilized, making the conjugate base weaker, so it's acid stronger. Okay, so we got that. Now let's look at the nitro group again, but in this case, we're going to look at it in terms of a different reaction. And I want you to be able to do this. I know it can be a little bit confusing at first, but you can do it. Okay, so now I want to look at this reacting not as an acid. I want to think of this as a nucleophile in an electrophilic aromatic substitution. So in this question, I said, oh, how's the acidity affected by the nitro? Now I'm looking at how is the nucleophilicity affected. So I'm looking at the opposite than I was looking at before. So we already established this is an overall electron withdrawer, and it's one of our strongest electron withdrawing groups. Overall electron withdrawer, right? So how does that affect this as a nucleophile? Nucleophiles want to be negative, and the nitro is pulling away charge. It's going to make it a weaker nucleophile. So, and in electrophilic aromatic substitution, they use a term most often, instead of saying weaker nucleophile, which is completely correct, you'll hear most often, you'll say it deactivates. The nitro group deactivates that. For electrophilic aromatic substitution, we've learned that you can have activators and deactivators because the benzene rings are nucleophiles and they have an electron donating group. Overall, it's activated, it reacts faster. If it has an electron withdrawing group, it's deactivated and it reacts slower. And also we saw that you can have orthopara direction or meta direction. And I really want you to be strong with this, so you all should go do the mandatory extra credit, which is on our website under handouts, and this one here, electrophilic aromatic substitution. I got a new version here, so if you did the original version, check out the new version. You don't have to redo it, but you can get some new things. And this will really help you review the mechanism and talk about, oh, an electron donating group helps you react because it makes you more nucleophilic. Withdrawing group makes you less nucleophilic, makes acid stronger though. So you'll go through and you'll answer these questions, and it'll be very helpful. So I want you all to do this. This is the best way to do it. And let me also show you our chapter 16 PowerPoint slides, which are online on our website here. no, lecture PowerPoints right here, chapter 14 to 16. So check that out. I'm going to look at some of that right now. We have already looked at it a bit. We looked at this slide before where we talked about these groups on the left-hand side are all orthopara directors, and some of them are activators, strong, moderate to strong activators. Some of them are still orthopara directors, but they weakly activate, and others even deactivate. So they react slower than benzene, but they are still orthopara. And then the meta-directors all happen to be deactivators, and none of them, you'll see, have lone pairs like that. So let's look at an example. So I have this PowerPoint slide up that I was telling you, right? It'd be very good practice for you to go through drawing all the lone pair electrons on these and then add the curved arrow mechanism. Like you're going to protonate, oh, actually you're going to protonate that oxygen, right? And then it's going to be a push-pull reaction where you get your super electrophiles. And now how is this alcohol affecting the reaction? It's got a lone pair that can resonate in. It's electronegative, so it draws out through induction, but overall it's a donor, so it's an activator. And what kind of actor? An orthopara directing actor. And if you fill in all the curved arrows and everything, you'll see when you put the nitro group ortho, you'll get this extra, if I drop a lone, you'll see it when you do it. You'll get this extra all-octet resonance, makes this lower in energy. Where the meta attack, it only has 1, 2, 3 resonance structures, not 1, 2, 3, 4. The para also has 1, 2, 3, 4 resonance structures, and it has less steric hindrance. So that's why this oxygen is an orthopara directing orthopara directing activator. So you get mostly ortho and para, but a little more para. And then I have the reaction coordinate diagram here for the key step, the step where the super electrophile gets added. When it gets added meta, it's a higher energy intermediate. When it gets added ortho, it's lower, and para is the lowest. So you can see the activation energy for the para is going to be lowest because the transition state, it's a late transition state. It looks more like products. So it's going to look more like this para intermediate. And then, yeah, you get the all octets for those. So fill all this in. It's well, this one's already pretty much filled in. You can add the activation energy arrows, but fill these in. This will be good practice to see it. And then I have a meta attack. Another group here. So what kind of a director is this? So it doesn't have a lone pair there, but has a pi bond. So hopefully you're thinking, oh, meta director. And it is a meta director. And because it can withdraw electrons from the ortho and the para positions more than the meta. And then also when you look at the resonance, the ortho attack gets you a bad resonance structure. Meta doesn't, and then para gets you a bad. So meta is the best case scenario, and if you were to draw up this kind of diagram, meta would be lowest energy. You should try to draw it up for this one. Another thing about this, oh yeah, so this guy is a meta director, this ester, when it's connected directly to the carbonyl to the benzene ring. And is it an activator or a deactivator? Well, let's see. It can withdraw through resonance. And this is an sp2 carbon, it can withdraw through induction. So overall, electron withdrawing, that makes nucleophiles weaker. It's a deactivator. And then here's some experimental data. So you see, if you have a benzene ring where R is your variable, my R here, and I just put an H on there, that's my reference. Just straight benzene nitrating. When you nitrate with straight benzene, it has a reactivity rate of 1. That's what we're going to compare everything to. And then when you put a methyl on the ring, what's this methyl? It's an sp3 carbon. It's electron donating through induction. Doesn't have resonance, so it's overall donor. And so guess what? It's going to electron donate into the ring, make the nucleophile stronger. It's going to react 25 times faster than benzene. Where the alcohol, it's an interesting one. You'd think the resonance when the alcohol is up here, the resonance in through is donating in, activating it, but induction is pulling out. So they're battling each other, but the resonance still is much more dominant, so it reacts 1,000 times faster than benzene, whereas the methyl only 25 times faster. It's interesting, huh? But that's what we got to go with the reactivity, the experimental data. That's what we base all our theories on. And then this is cool too. So the methyl group by itself is electron donating overall a little bit. You take a methyl and you add a chlorine to it, chlorine's electronegative, and so it's increasing the induction. So this actually turns out to be an electron withdrawer, so it's slightly deactivating. And then the iodide, it donates in through resonance, but withdraws through induction, and its induction wins out slightly. And then you can see as you go down the line, the nitro is a really strong electron withdrawal. It really slows the reaction down. And then you see the ortho-para stuff too. So like when the alcohol's here, you get mostly ortho and para. And the methyl is a weird one. It doesn't have a lot of steric hindrance. So you do, this is the one case I've seen where you get a little more ortho than para. I'm not going to try to trick you with that. But if you think about it, there's two different orthocarbons that it can react at. So if I want to compare the reactivity of these two orthos to just the one para, I should divide 58 in half and compare it to 38. So when I divide 58 in half, I get 29 of each ortho product. So that actually, it's still more para directing, right? Okay, so you can look at the other ones and like the nitro, you can see it's very meta directing. Nice, huh? We'll talk about these shortly. Let me get back to my outcomes and get back on the, oh, before I do that, actually, let's go back to this one. So it's a nice thing to notice, general ortho-para directors, they usually have a lone pair. The alkyls don't, but most of them have lone pair right there. When you see that lone pair, you think it's going to be an ortho-para director. If you see no lone pair and a pi bond coming off, that usually means it's going to be a meta director. So that lone pair, focus in on that, and then I'm going to bounce in the pi bonds, so focus in on that. So if you get used to seeing those, it's easy. So what do I got here? Does this carbon here have a lone pair on it? Nope. Does it have a pi bond coming off there? It does, huh? This is a meta director. It's a deactivating meta director. What about here? I have an ester. Before I had an ester a little while ago, and it was a deactivator or the meta director. But what about this one? The lone pair, huh? Boom, it's an ortho-para director. And it can actually donate in through resonance, withdraw through induction, resonance wins. It's 2p, 2p, good orbital overlap. So this is a ortho-para directing activator. And then finally, this one, does this carbon have a lone pair? No, the nitrogen does, but it's got to be the atom directly on the ring. So what is this guy? It's a meta director. And it's going to withdraw through resonance. And this carbon's sp hybridized, so that's more electronegative than hydrogen. It's withdrawn through induction and resonance. Overall withdrawer, it's a meta-directing deactivator. All right, that's some old stuff. Now let's get back to our chapter outcomes. Same thing we're just doing. The England stuff, we'll go into this all octets again for you, and the meta, bad, very poor resonance. So now let's talk about some details of our reactions, and I'll do some examples for you as well. So as I said, ortho-para directors generally give you more para, and you can think about it in terms of sterics and induction maybe, because the induction withdrawing would be weaker ortho than para. And we talked about blocking this with sulfonation, because that's a reversible reaction. So let's try an example of that one. Imagine you have this molecule here, this is acetate-aniline, and say you want to make this into a molecule with the orthobromine and only orthobromine. You don't want any para. How could you go about that without having to worry about getting any para there? Well, you can use the sulfonation reaction, which is reversible. First, let's look at what this guy is. This nitrogen here, through induction, it's withdrawing. Through resonance, it's donating in, so it's battling between induction and resonance. Resonance is very strong because it's a 2p, 2p. It's an overall electron donor. And so that means that it will be an activator. And is it an ortho-para director or a meta director? It will be an ortho-para director, right? Ortho-para directing activator. But what is it more of? It's more of a para director. More para director than ortho. So, I want ortho, I don't want the para. What am I going to do? Well, what I'll do is I'll first put on the sulfonation, or the sulfonic acid para to block that position, because I can take it off afterwards. Let's do it the right way though. Let's do retro. Let's say in the retro of this one, we would have our ortho product. That is going to come from the sulfonated, basically that protected, para-protected product. So I've got a sulfonic acid down there. And this came from then the parasulfonic acid. So the parasulfonic acid was made first, and then the bromine was added on afterwards with this sulfonic acid blocking that position. And then you can see, okay, this just comes from the original given amide. So let's do the synthesis. We have our acetanilide here, and this molecule is an orthopara-directing activator. And if I add fuming sulfuric acid, I can sulfonate mostly in the para position, which is because this is more of a para-director. And I get some ortho to purify that away. This is my major product though. And now I can say that the para position is blocked. It's interesting, you could say the para position is protected, but in this electrophilic aromatic substitution chemistry, they tend to use different words like activating instead of a stronger nucleophile, blocked instead of protecting group. It's okay, it's all the same stuff. All right, so now at that point then, since that's blocked, if I add a bromine and the iron 3 bromide, what do I get? I have for this one, for the amide, it wants to go ortho right there. My sulfonic acid, what is it? It's a meta-director. So relative to its ipso, where it's attached, it wants to go to the same carbon. That's meta for it. So this is good. This here, the sulfonic acid is a meta-directing deactivator because it's withdrawing overall. But we have an activator here, so it's okay. All right, so we're gonna brominate that ortho position. And now that we have our bromine just ortho, there's no parabromine, we can deprotect or deblock by adding water instead of just concentrated sulfuric acid. You add water and sulfuric acid and you heat it up. H2SO4. And that will remove your protecting group or blocking group. You have just the bromobenzene. Now moving on, after learning about using the sulfonation to block or protect a position, let's look at when we have an orthopara-director and a meta-director on a ring and they don't agree with each other. On the example we just did, we had an orthopara-director and a meta-director, but they agreed to try to add groups to the same carbon. If they don't agree, then it turns out whoever's the strongest activator, or say if you have two deactivators, the weakest deactivator, that's going to dominate where things go the most. Let's look at examples of that. And then we're also going to look at, there's a lot of details with this stuff, and I'll just mention it here too. We'll look at, like, when you have an activator like an amine or the alcohol, they're so strongly activating that they might activate the ring multiple times. So we'll look at a couple examples for both of these. On this first example, I have the methoxy group here. It is a ortho-para-directing, strong activator. It would be similar to the methoxy, the phenol we saw in that table from the chapter 16 PowerPoint slide. So it should react like 1,000 times or something, maybe more, faster than benzene. Okay, so that one's ortho-para director. So it wants to put things relative to its ipso position. It wants to put an ortho, or para. That's where it wants to put groups. Whereas the ketone here, that one is a meta-directing deactivator. So it wants to put things relative to its ipso position, meta, or meta, but that meta position is already blocked. So they don't agree. So who's going to be the one that determines where the major product is formed? Well, the activator will win out. The activator dominates. Because the deactivator is saying, oh, I'm going to deactivate meta, but I'm going to deactivate these other positions more. It's like just negative. You think of it, it's always negative no matter what. And then, not negative, that's not a good thing because it's the negative electrons. But it's, the meta-director deactivates its ortho and its para a lot, and then its meta, it deactivates less. Where with the ortho-para director is activating its positions in. It turns out that it wins. Kind of just feels intuitively right. So your major product for this one is either going to be ortho, para. Normally the para wins out, but there is steric hindrance issues too. So I'm going to say though, not easy to tell on these ones, but I'm going to guess para is going to win out because I think the steric hindrance of this group is similar to that. So I'm going to go para would be major on this one, most major. So I'll nitrate there. I'm going to say most major there. And then I would say the next most major will be the ortho that's not so much steric hindrance. And then that would be the third, and this would be your minor product there. Okay, and now for the other one I got up here, I've got different groups on here. Let's work through it. The first one there is this amide. We saw this already in an earlier example. This is an ortho-para directing activator, very strong activator. And then the methyl here is an ortho-para directing weak activator, but it's still an activator. So that's nice, right? And so relative to the methyl, it's ipso here. It wants to put groups ortho, but para is blocked for it. And then the amide, it wants to put things relative to its ipso, ortho, but the para is blocked. So they're not agreeing. But who's going to win out? Well, the amide is one of the strongest activators, a very strong activator. So I kind of want you to remember this is a stronger activator than methyl. I want you to remember the alkyls are weak activators, but I'm not going to probably focus my exam questions on that. I'll maybe give you evidence of that, but we'll just do a lot of examples too. So the major product should be predicted to be product in which you put the, this is a Friedel-Crafts alkylation, where you put it ortho to the amide. when you're reacting aniline, it's a very activated ring. So this here aniline is an orthopara director and a very activated. So it's strongly activated. So let's say you want just the monobrominated product, and you want it para. It's challenging to get it to be there, to only get the mono. Because what you wind up getting is it just keeps adding because it's such a strong activator. Even though the bromine's a weak deactivator, so this will react slower than that, but it's still, you'll wind up getting a lot of bromination. And you'll notice I put this bromine ortho to the nitrogen because that's the stronger activator. This is a weak deactivator. And then it can continue to give you the tribrominated product. Whereas if you have an amide instead of the amine, this sort of tames it a little bit. A bit more tame. Not as strong of an activator. So actually most often you don't use this, you use this because this is just so reactive. And so this reaction you can get, it'll be easier to get just say the monobrominated product. And then after you get the monobrominated product, you can remove this. And we'll be learning about that in future chapters. Yeah, you can use either acid or base to cleave that and make it back into the NH2 with acid. Yeah, say if you use base, you can bring it right into the NH2. So there's considerations like that you have to think about. Well, why is this taming it? Because remember, what makes this an activator is that the nitrogen wants to drop its lone pairs into the ring, right, and donate. Now, with it being an amide, it has competition. That pair of electrons is also being pulled towards the carbonyl. So it's not as strongly electron donating through resonance. It's still donation strong enough to override its induction withdrawal. But it's interesting, right? All right, for some more details about this stuff, if you try to say nitrate aniline, something interesting happens. When you look at this, you're probably going to predict it's an orthopara director, and your major product will be para. But it turns out in this reaction, your major product has the nitro group, not para, but instead meta. Why is that? This is a big clue. Because what happens is under these very extremely acidic conditions, the nitrogen gets protonated first. And once it's protonated, this no longer has. So for this one, it no longer has a lone pair to resonate in. It can only withdraw through induction. And that induction is very strong because nitrogen is an electronegative atom. Plus it has a positive charge. So this one's a meta director. If you use this here, it works out okay because the nitrogen lone pair is much less basic now. It actually resonates into here, and if anything, this is can be protonated. So that's how you can add things para with the nitrogen. And then here's another interesting one. If you try to alkylate this, you start with the benzene, you put on your first methyl. When the methyl is added, what happens? It becomes an orthopara directing activator. So after your first methyl is added, your toluene product is more reactive than the benzene it started from. So it's going to start to outcompete. So it's going to add another methyl, ortho and para. You'll get, in this particular case, a little more ortho because there's 2 ortho positions to go to. And now it's doubly activated, but do they agree? No, they don't agree, but it's still got a lot of electron density going to it. So it could get another methyl added in here. So it could be a challenge if you're trying to alkylate with Friedel-Crafts alkylation, that after one group's added, it makes more reactive. The opposite is true of something like, say you want to nitrate a benzene ring. Once you've nitrated the benzene ring, it's much less reactive, so there's not a big concern about over-nitrating it. Because now this is much less reactive than the original benzene. And true of any, like if you brominate, the same thing. All right, just a few more things to finish off chapter 16. There's a lot of details you can go into on this stuff. This is a real rich chemistry, the electrophilic aromatic substitution chemistry. And it can get to be much, so I'll tell you what I'll do. I'll give you some reactions you can use, but what I'll do is I won't make you have to memorize them. So for the exam, you'll be given this as like kind of like you're given the periodic table. You'll be given these 4 reactions here. So let me explain them a little more though. So it turns out you could take a nitro group on a benzene ring, which is a meta director, and turn it into aniline, which is an orthopara director. So you can switch them. Same with a ketone, which is a meta director. You can make it into an alkane, which is an orthopara director. And let's look at those reactions down here. So this is from our outcomes once again. So the ketone, you know, is a meta director, deactivator. You can reduce it with what's called zinc amalgam. When you say amalgam, you mean something dissolved in liquid mercury. So when you dissolve zinc in liquid mercury, it's a zinc amalgam. Sort of like when you dissolve sodium chloride in water, it's a sodium chloride aqueous. So mercury, you say amalgam. So it's a zinc amalgam, and then HCl and heat, and you can actually take off the complete oxygen. Isn't that cool? And this works for the ketones that are directly attached to the benzene ring. If the ketone's further down the line, it doesn't work as well. So you can take this meta director and make it an orthopara director. And if you have an orthopara director, you can actually take it back. Orthopara director alkyl group like this, you can put back on the ketone with an oxidation, with Jones oxidation. There's something special about this benzyl position right next to the benzene ring. It's remember, if we put like a radical there, it can resonate into the ring, but carbocation resonates with the ring, and same with an anion. So it's more reactive. These benzyl positions, they're like allylic positions, but they're called benzylic positions. So you can take an alkane and make it into a meta director. And for the exam, you'll have this document in front of you. So if you need this reaction, boom, you just use it. And then you could take a nitro, which is a meta director, deactivator, and you can make it an aniline, which is an orthopara director. This is actually a reduction. You could do it with it's pretty much the same as the reduction of the ketone here. That's one way to do it. There's lots of ways of doing these things, but you can use the zinc amalgam and HCl. And then you do a second step with sodium bicarbonate, because under these acidic conditions, this will be protonated. And then if you add a base like this, you can deprotonate it. And then finally, you can reverse that with, you can take the orthopara directing aniline and make it into the nitrobenzene with a weak oxidizer like this. This is I don't know if it's weak, but this is trifluoral peroxyacetic acid. See how it's got O3 there? This is a peroxy acid that you can use to make epoxides and things. But it won't make an epoxide out of these pi bonds because they're aromatic. They're a lot less reactive. But you can oxidize that way. So you got these 4 reactions that you'll have a sheet to work with. So I'll do an example with those now. But before I do, let me just mention these. There's a few more details here. I'll let you read these over yourself, and I'm not gonna try to throw these in there to really trick you up. But if you read through them and try to understand them, you're gonna gain a lot of knowledge about this. So let's just do an example with these guys, and then we'll be done with chapter 16. We'll move on to chapter 17, aldehydes and ketones. We got some good ones here. This one, I like this one. This one's kind of tricky. Let's see how it goes. When you start off with it, it looks like you've got a meta director here. And it's a deactivator. But the main thing we have to consider is a meta director, but our products are para. So it looks crazy, like, wait, meta director, and I got the para there. What's going on? I can use any other carbon source. Well, let's just try working back from this guy. So I got my ketone on the top, my alkyl chain on the bottom. When I'm going backwards in the retro, I should say, they're para to each other. I should have the para or the para director on there, and then that gets added on later. So let's do that. Let's say I have and that can be my any other carbon source. Okay. Now I gotta ask myself, can I get this from my beginning thing? And I can, huh? See what it was is it was just twisted around. So this is equal to that, right? Which can come from the Clemmensen reduction of that ketone we started with. Okay, so let's try the synthesis. You'll see it clearly then. So I start with my orthopara-directing ketone. And I have to reduce it to the alkane. And I can do that with my Clemmensen reduction. You don't have to have this mechanism, this reaction memorized, and we're not going over the mechanism either. But you'll have a table on your exam and it'll say, oh, I can use this. Zinc amalgam, HCl, and heat, and it will reduce this to an orthopara-directing alkane, propylbenzene. So I want para ketone there, so I use the Friedel-Crafts acylation or alkylation or alkylation. No, yeah, that's right. And I got my target molecule. That was all I needed. Just a two-stepper. It's tricky though how it was twisted around on you. That's what I like about this one. But if you do the retro, it shouldn't trick you. Okay, and now this one is almost cruel and unusual punishment. Got a lot going on here, but it's good. We can get through it. Let's do it. So we got our retro first. Let's draw this beast up. Got a cis alkene. Hopefully that rings a bell for you. A cis alkene, that sounds like partial reduction of an alkyne, right? So we can see where that alkyne's coming from there. And then this is, we can see the carbon-carbon bond forming there too, huh? And we've got, oh, you know what? I should have gave you this to begin up here, huh? Sorry. All right. Nitro and also the alkyne anion, which can come from just the alkyne, which I gave you, which you could have made too, but this is already a long one, so I gave you that much. Okay, and now this guy, we see, I've got a meta director and another meta director, but they're ortho to each other. Yeah, so something went on there, huh? Meta. So what's going on with that? That means one of those had to be an orthopara director. Let's go with the ketone. Let's say that ketone was an orthopara director. It was the alkane, say. So, okay, I can get a nitro ortho to it, but how do I get the nitro just ortho and not so any para? This came from the blocking group. Pretty awesome, huh? This problem was not messing around. And that nitro group then was put on after the sulfonation blocked para. That came from the ketone, which came from the benzene. Whew! And the acid chloride. Brutal, huh? But if you can follow along with me, you're doing really well on this. That one might be, I don't know, you can do that. You can have that on exam 3, we'll see. It's a tough one though. It's stout. What do you want to deprotonate that alkyne, terminal alkyne with? Maybe sodium hydride? That'll work. Maybe a THF. Yep. Any strong base. Stronger than hydroxide, of course, but just remember the pKa of this is 25. You make hydrogen gas in this one, its pKa is 40, so that's product favorite. So we'll pause there and then start on the other ring. So we gotta put on our ketone first. Friedel-Crafts alkylation. Then we reduce it to the alkane. We'll use the zinc amalgam, HCl, and heat. And now we're going to block the para position, fuming sulfuric acid. That's the para director. Has more steric hindrance than just a methyl, so it's going to produce more para. Then we can add on the nitro group, just ortho. I'm gonna put it over here, I hope that doesn't bother you. And then we can remove adding water, sulfuric acid, and heat. And now I need to get my ketone back. So how do I do that? Jones oxidation. That's on the list of reactions that you don't have to memorize. Okay, so we're almost there. We got our ketone. Orthonitro. We add in our alkyne anion we made way back when. An acidic workup. I'm writing pH to abbreviate phenyl there. And I got my nitro here still. Finally, you do the reduction with hydrogen gas and Lindlar's catalyst, because that will give you the partial reduction syn addition, giving you this syn alkene we were looking for. So bam, that's our target molecules. Whew. Chapter 17, here we are. We have just been spending a lot of time with those aromatic rings, taking a little bit of a break, trying something new. It's actually it's new, but it won't feel totally new because it's we've been looking at aldehydes and ketones a lot. Now we'll finally formally learn how to name them, and you'll notice that it's interesting when you have more than one functional group on a molecule. You have to decide how you want to name it. These are just rules made up by the old chemists at IUPAC arguing over what's higher priority and lower priority. So for instance, an aldehyde is considered a higher priority than a ketone. So if you have an aldehyde and a ketone on one molecule, you'll name it as an aldehyde, not a ketone. But now, before we go into too much detail about that, let's look at what we do. So if you have an alkane and it becomes a ketone, the E part of the alkane goes to -one, so E to -one. For an alkane as an aldehyde, you get E goes to al. So like octane could be 2-octanone or octane 2-one and octane octanol. Let's look at a couple examples here. So that was from earlier. Let's make up a ketone like here. Put a methyl out here. Throw in the oxygen. Let's see what the name is. Let's guess actually first. 1, 2, 3, 4, 5, 6. You think it's going to count that way, or is it going to go 1, 2, 3, 4, 5, 6? I'm going to guess it's going to count in the way to give the ketone carbonyl carbon the lowest number. Let's go structure to name, and let's say okay. Oh, it's naming the water over here. Let's get rid of that water. What? Never mind. Let me highlight it. Structure to name. There it is. Let's see. There it is. We're going 5-methyl. 1, 2, 3, 4, 5-methyl. 2-hexanone. 6 across. Instead of hexane, the E becomes 1 basically, but you pronounce it -one. Or you can call it 5-methyl hexane 2-one. I usually use the top method, but either way is fine. All right, well, let's try now an aldehyde. For an aldehyde, you need to have the carbonyl at the very end of the chain, right? And we usually show the hydrogens. So there's an aldehyde, and it has, we'll throw some stereochem on this one, why not? I usually always throw a stereocenter in these times. So this aldehyde, what do you think? What's the longest chain? 1, 2, 3, 4, 5 carbons long. And it's got a methyl there. Is that R or S? Let's look A, B, C. It looks like R. So I'm going to go 2R, 1, 2, 3, 4, 5 pentanal. 2R, 2-methyl pentanal. Let's see. Structure to name. Paste it. 2R, 2-methyl pentanal. Instead of pentane, the E became L. Not too bad, right? Okay, back to our you know what? I'll do one of these preferences ones. Okay, so let's say I throw on an alcohol. So do I name this molecule as an alcohol, or do I name it as an aldehyde? Let's look at our priorities here. Aldehyde's this priority. It looks like it's greater than an alcohol, so this is going to be called an aldehyde, named as an aldehyde. So it'll have, instead of being like a pentanol, it's going to be hydroxy pentanal. Let's check it out, make sure we're right. So if I go structure to name, boom, look at that, 2R2 hydroxy pentanal. So the aldehyde took precedence over the alcohol. Now that's it. This isn't anything to do with nature. This is just humans made up these rules. And I'm not big on testing you on this stuff real hardcore. Just notice, like, basically if you have a carbonyl, you outweigh the alcohols and the other things. So, all right. So let me go back to that. And now carbonyl-containing compounds are electrophiles. We've seen that a lot. Grignards and lithiums attack them, and we saw sodium borohydride attacks the carbonyl carbon, lithium aluminum hydride. We've seen a lot of things, right? Alkyne anions. So we've seen them be aldehydes, electrophiles a lot. And look at this. It says the aldehyde is a stronger electrophile than a ketone. Let's check that out. Why would that be? So I've got an aldehyde up here. And now let me drop a comparable ketone. So I got my ketone, got my aldehyde. How do they differ? Well, they differ here. One side of the carbonyl carbon on the aldehyde has a hydrogen, and this side has a sp3 carbon. For the ketone, you have an sp3 carbon and an sp3 carbon. So what do you think? Who is going to be more electrophilic? It's going to be the one that has the most positive charge about it. So let's try this. I'm sure you can agree they should both have a delta positive charge here. So there'll be a delta positive for the carbonyl carbon. That's what makes it a good electrophile. But is one going to be slightly more positive than the other one? Yes, the aldehyde will be a little more positive. Why is that? It's because over here we got an sp3 carbon, which is by induction electron donating relative to the hydrogen there. Remember, an sp3 carbon is less electronegative than a hydrogen. Nice, huh? So that's going to donate a little bit of electrons to the carbonyl relative to the hydrogen, so it won't be as positive as the hydrogen. And then the reason why these guys are even positive is because the oxygen is very electronegative, right? It's this electronegative oxygen here that's causing this. And boom, 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 something like that, right? Nice. So the aldehyde is more electrophilic than the ketone, just slightly. And this is just like we learned in electrophilic aromatic substitution. It's pretty cool how it all ties together, huh? Okay, now back to our list of outcomes. We're going to find, it's interesting, the carbonyl is reactive at its carbonyl carbon as an electrophile, which you've seen already. It's also electrophilic if it has alpha-beta unsaturation. It can, electrophiles or nucleophiles could attack the beta carbon. It's pretty interesting. We're going to see this where a nucleophile comes in and this pi bond hinges on the alpha carbon, swings up, puts a negative on there, so you can add there too. I mentioned that on a lot of your exams. I said you'll be learning about that later. We're not going to focus on it just yet, but this is just a nice summary for the next couple chapters. We're also going to see these alpha carbons that aren't alkenes. They're pretty acidic because they have resonance to the carbonyl. We'll see that. We've already seen enolates like that, but we're going to see them more. And then if there's an alpha-beta unsaturation, we'll talk about this. This guy's even more acidic, and we'll see why that is. Before we get into that, though, let's just review really quick. You know, aldehydes stand out. Aldehydes and ketones both have the alpha carbons around 2.1-ish. But the aldehyde has a 9.5, so let's look at this guy. So on the proton NMR, this guy has a signal at 9.5 parts per million. That's what makes it stand out. They both have the about 2.1 parts per million signal for the alpha carbons hydrogens. So they're similar there. This would have 2 of those type of signals, the ketone. And then in the carbon NMR, they both show up around 200 parts per million. The carbonyl carbon. So you can't really tell them apart in the carbon NMR because they both show up around 200 parts per million. But the proton NMR gives it away. And the IR, we have the carbonyl 1700. They both have that. Okay, and then looking good there. Mass spec, they can both do alpha cleavages, and if they're long enough, they can do the McLafferty. So how do we make aldehydes and ketones? We've done this a lot. Review this stuff. You can oxidize alcohols with PCC to make the aldehyde if it's a primary alcohol. Ozonolysis, you can cleave alkenes and get aldehydes or ketones. Hydration of alkynes can make you a ketone or an aldehyde. Oh, this can only make a ketone, actually. The dicyclohexylborane anti-Markovnikov hydration of an alkyne can make you an aldehyde. And then you can make ketones on the benzene rings with the Friedel-Crafts acylation. And then we know that these aldehydes and ketones react with nucleophiles. So review all those. Try to make up an example for every one of these, different than the one that's given. That'll be a good review for you. And it's nice to see things like, oh, ketone and a Grignard or lithium gives you a tertiary alcohol, but when you use an aldehyde, you get the secondary alcohol. And formaldehyde gets you the primary. So check that stuff out. And the next thing we'll talk about is this selective oxidation with MnO2, manganese 4 oxide. Let me pause for a sec for that.